Hi all, I hope you are doing well today. We are moving on to Unit 6, Lesson 7. We're doing Applications of Electrostatics. So for today, you're going to need your notebook, pen and pencil, and your classwork document open and your Google Classroom open. Okay, so today's lesson is mainly practice, and it's a practice-based lesson, and we'll be practicing all the concepts from previous lessons in this unit, and we're going to apply them to different scenarios in order to test out our thinking. During this lesson, it will be helpful for you to have your notebook out so that you can refer to previous examples and key points. It will support you as you do your work through today's practice problems. Okay, so before we move on to doing practice problems, we're going to watch a quick video on the law of conservation of energy, and then we'll go over some key points, some practice problems, and then an exit ticket. All right, so let's start with Arjuna. So consider the question that's in front of you. In your classwork document, take the next minute or so to answer this problem. Consider how you would approach solving this. So we haven't done something like this yet, but we have seen different examples that can relate to this problem. Right, so take the next 2 minutes to try to solve this, and we'll gather back in a few. Right, press play when you're ready to start again. Press pause now. All right, scholars, welcome back. So we are going to, I'm not going to give you the answer exactly on how to do this right now. It will become clearer as we go through the lesson, right? And we'll revisit this. Before we move on to watching this video I mentioned, I wanted to discuss a few vocab words that you probably have heard of before, but I just wanted to make sure that we understood what they are. So first, the first two vocabs are a conductor and insulator. So this both refers to materials, right? So a conductor is a material in which electrons are able to flow freely, and an insulator is a material in which electrons are stuck and they're not able to move. And in front of us, we see a few examples of that. Right? So more examples of conductors are metals, so silver, gold, copper, steel. Seawater is also a conductor. Water in general can be a conductor, so that's why it's really important to keep electronics away from water. And that's also the reason why if there's a thunderstorm and you're at the beach or at a pool or something, usually lifeguards ask everyone to come out of the ocean because it can be dangerous if lightning strikes a body of water. And then materials that are insulators are rubber, glass, oil, diamonds, wood. And so that means that electricity won't flow easily through those materials. Right, so I'm going to show you guys, keeping those vocab words in your mind, it will be a little easier to understand this video. We're going to watch the first 3 minutes of it. This Bozeman video, he's going to explain to us what the law of conservation of energy is, and the key points from this video are going to help us solve the problems for today.
Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 91. It's on the conservation of electric charge, and this is among objects inside a system. And we're going to start with a simulation. This is from simbucket.com, a group of physics teachers in Illinois. And what I'm going to do is take a balloon, I'm going to rub it on a sweater, and what it's going to do is it's going to pick up the electrons. It's going to pick up a negative charge. Now, if I hold that next to a conductor, like a bucket, it will be drawn to it. And the reason why is that it's pushing those negative negative charges away, which can move in a conductor, and so it's drawn towards the positive charge. If we look at an insulator, those electrons can't move throughout the material, but they can move on either side of the proton, and so then we can get that positive charge and that attraction. I can even touch it, and through conduction we can transfer some of those charges to the object as well. But the number of charges that we have in this whole system is going to be conserved. It's going to remain the same over time. And so the conservation of charge in a system means that if we have a couple of objects, one let's say is neutral and the other one is charged, if I bring that charged object next to the neutral object, I can induce a charge in it, but we're not bringing in new charges, we're not losing charges, the amount of charges in the system is going to remain the same. Even if I touch that other object and there's conduction, so the movement of charges, the total amount of charges in that system is going to remain the same. And so how can I ever lose those charges? Well, a really easy way to do that is through grounding. If I conduct those charges away to something like the Earth, then we can actually change the amount of charges inside the system. And so an example of this, if we take some amber and we rub it on some wool, what we're really doing is we're transferring charge from the wool to the amber. So if I hold it above a feather like this, the feather is attracted. And so now let's look at the conservation of charge in these objects. This is what all the objects look like before, and I made it as simple as I can. So they both have a net charge of 0. All of them have a net charge of 0. In other words, the positive and negative charges are going to be exact.
Take a close look at this example that he's given and make sure to write down any key points in your notebooks.
The same, but when we rub that amber on that wool, what we're doing is we're transferring some of those electrons to it. And so if we were to look at now this wool here, it has a +3 charge, and this is going to be a -3 charge. We've transferred those electrons to the amber. What happened to the total number of charges before and after? They're exactly the same. We've just moved where they are. And so when you hold that amber above the feather, what it's doing is it's inducing charge inside the feather, and so we get a positive charge on one side, and that's why it's attracted to the amber. So we could see the same things through conduction. So let me charge up that amber again, and I'm going to use a pith ball. So the pith ball, same thing as the feather, it's going to be attracted to it, but it
just really quick, pith ball is just a little ball made of aluminum, so it's made out of a metal. Oops. Sorry about that.
Held. Why is that? There's conduction. We're actually transferring some of that charge from the amber to the pith ball. Now they both have a similar charge and we get that repulsion. So let's look at the conservation of charge here. So they all had a net charge of 0 to begin with. We transferred some of those electrons to the amber, but we then transferred some of those electrons to the pith ball. And so at the end, this has a negative charge, this has a negative charge, and so we have a repulsion between the two. What happened to the total number of charges that we have? It's conserved before and after within the system. Now, how can we get rid of some of that charge? You can see that we have an excess.
Okay, so we're going to stop here. The important point to make from here, so please write this down, is that charge is conserved, meaning electrons will move from one object to the other, but they don't just appear out of nowhere. Right? It was the same with when we learned about the concept of conservation of energy, that energy will move from one object, will be transformed from one object to the other, but it can't just be created. So similar idea. All right, so let's move on. This is actually the key point, so you can write this down into your notes. In order to apply the law of conservation of charge, you need to find what the net charge of a system is. That net charge is not going to change, right? That's the whole idea of conservation. If conducting objects are brought near each other and then separated, they will have a new charge that is the net charge divided by the number of objects. So to make that a little clearer over here, we have this object where this rod has a -4 charge. And then over here, this one has, this object has a charge of 0. Right, so then this is before and then after. So they touch and then they're separated. And then the charge gets equally divided into both. Okay, so this is really important. Before we move on to our practice problems, let's do this quick check for understanding as a group. So take the next minute to solve this problem in your classwork document, and then we'll come back to answer this together. Right, you can press pause now so you can work on that. Alrighty, so let's check to see what our answers are. So here we have a metal sphere that has been touched by a negatively charged metal rod. During the process, electrons are transferred from, so here we have this rod that touches the ball. So then the electrons are going to transfer from the charged rod to the neutral sphere. Right? And then by doing that, since this is neutral and negative charges are moving onto it, the sphere acquires a negative charge. So our answer will be C. Okay, so go ahead and revise your answers if you had something different. Okay, so now let's move on to our practice problems. So you're going to take the next 5 minutes to solve problems 1 through 2 in your classwork document. Problem 2 will actually require you to draw force vectors, so you can draw this in your notebook and submit a picture, or you can just also verbally explain that the vector will be pointing to the right or to the left if you don't want to take pictures of your notes. Right, once you've completed with the second problem, you can press play again so that we can go over something before we move on to the last problem. All right, so 5 minutes and press pause now to start. Great, welcome back. So before we move on to the third problem, let's double check our answer for 2A, the first one, so that we're all on the same page on how to solve this problem. Okay, so in the chat, or I'm sorry, what answer did you get for this? Right, so let's discuss what we have here. So in the question, you're asked to find the direction of the force that's being applied on B. So let's look at the charges that are next to it to see how they're going to influence B. So B is positive, and A is positive, and C has a negative charge. So we know that positive and negative charges are attracting to each other. So then that tells me that B is most likely going to be moving towards A in that direction. Oops. And then we also know that positive charges repel. So if A is positive, then B is going to be moving away from A. So then our force vector is going to be moving towards the right for B. Okay, so hopefully it clarifies your answers, and if you need to go back and double check your work, go ahead and do that now. Okay, so moving on to another key point. If there are, that relates to this problem, if there are 3 charged particles in a row, I can find the net force on the middle charged particle by determining the force on this particle by either of the outer charged particles and then comparing them, right? So that's exactly what we just did in the way that I modeled the problem right before. Okay, so now let's continue our practice. So on your own, solve problem 3. Again, problem 3 will require you to draw some force vectors, so you can draw these into your notebook and submit them as a picture in your Google Classroom afterwards. You take the next 5 minutes to solve problem number 3, and when you're done, press play to join us again. Alrighty, moving along. So the core idea for today's lesson is that Coulomb's law and the law of conservation of charge both help us make predictions about how charges will behave and will help us make sense of how charges interact after we have observed their behavior. When comparing different charges, it is important to consider Coulomb's law, the law of conservation of charge, and electric field strength to support you in making informed predictions or explanation about a phenomena. And so the purpose behind learning all of this is that it helps us be able to predict behavior of electrical charges. Moving along. So for our exit ticket, I'm going to take the next 5 minutes to answer the exit ticket that's late in your classwork document. Once you're done with that, you can submit your classwork in your Google, submit all the work that's in your Google Classroom. And if you took any pictures of your work, then make sure to upload that as well. And don't forget to submit it by the end of the day. I hope you all have a wonderful day, scholars.